Hello friends. In the previous video, I solved an example problem, and that example problem was this. It was an example problem where we needed to calculate all the fields here. However, since we had to provide multiple things together in that example problem, if we count these, it included a Helmholtz equation, a boundary condition, and the application of Maxwell's equations, which made it quite a long video. I accept this. When I looked at my impressions of its length, I saw that many people might not benefit from it. Therefore, I decided to explain some of those situations here, separately, and in parts, so that you can learn briefly here and perhaps later endure the solution to that long problem. The first of these is a title called The Fundamental Logic of Boundary Conditions in Wave Theory. Why are boundary conditions important? We will discuss that, and how to write the equation of equality. Now there are two situations regarding boundary conditions here. One is the equality of electric fields at the boundary conditions. The other is the equality of the magnetic field at the boundary conditions. And these two can be examined in two different cases, electric field and magnetic field. One of them is the perfect conductor, which refers to two types of surfaces, perfect electric conductor and perfect magnetic conductor. Whether it is perfect or not is not a big problem. It only changes whether it is an electric or magnetic conductor. I will talk about that. There are also region transitions. That is, not all of the waves are reflected, as seen here. A certain part of the waves determines the state of the regions when passing through the second dielectric region, that is, the epsilons. When either epsilon or nu changes, that region automatically changes. Here, I might have taken the zeros for nu. It doesn't matter. The nus could have been different. It is sufficient for all of them to be the same while the anus are different. The medium to be directly another medium. Friends, let's not forget this. And afterwards, we have such a transition. That is a situation where part of the waves pass and part of them are reflected. There is also a situation where the entire incoming wave is reflected. Now for us, there is a slightly different situation regarding boundary conditions. Let's write that down if you want. Now friends, in the logic of this, it is written as follows: boundary conditions. At the boundary conditions, this is the transition point. Look, this is the y-axis. This transition point, where y equals 0, is a critical point for us. I wrote it this way. There is a change at y equals 0. There is a change at y equals 0. And it tells us this. If it is quite so, I will write separately for patch. I will write separately for PMC. PMC is not usually asked much. Generally, this is altered a bit in antenna and microwave questions. For now, I will. Generally, it is not very difficult, but to understand the logic, I am explaining how it works in both Page's boundary conditions and PMC's boundary conditions. Now, the logic of the event is as follows. A wave coming here completely reflects at this point where y equals 0, so the boundary conditions state that at the transition point, which is the first side where the field is located, if we say this side is the first side and this side is the second side, then the first side where the field is located and the areas where the fields are not present, because as you can see, since it extends from positive infinity to negative infinity, we know that there will be no wave transition here. Therefore, we know that the fields here are 0. If the field here is 0, then in a region very close to where y equals 0, isn't this field also 0? But there is also a field coming from here. The boundary condition tells us that at this exact 0 point, their t-component, meaning the cross operations, that is, n cross E1 should equal n cross E2, my friends. And here we know what E2 is, my friends. There are no fields here. E and H are 0. Since E and H are 0, where is n cross E1, my friends? Of course, it should be written here as well, at the boundaries. At the S surfaces, I'm writing S here. Look, is this the S boundary? Where is my boundary? Here, at y equals 0. It must be equal. Since on the other side, 0 cross 0 will be 0, it equals 0. Friends, this is the logic of the situation. So how do we expand this? I will explain that shortly. If you wish, this was the written form of your first boundary condition. So can't I write this here? Since n cross is 0, because the electric fields are completely zero in this region on this side, it has to be zero. So why can't I write this? N cross H equals 0. Let's say H is 1, N cross. Let's talk about why I can't say that H2 is 0 from here, and why this equation equals 0. So N cross H, in the first region Y equals 0, is not 0, friends, because when the material is an electric conductor, automatically the remaining N cross H gives the current density. Therefore, it is not 0. The same thing applies to this patch. The two boundary conditions I wrote here, meaning the general situation I can use is this, friends. I can use this for perfect electric conductor. I cannot use this because it is equal to Js. And the opposite situation. What is the opposite situation, friends? If this were PX, if it were PMC, meaning perfect magnetic conductor, let's write it down. These operations would switch places, friends. If it were P, M, C, again when you say NX, NX, E1, NX, E2, we cannot say that E2 is 0 this time. Let's write it down again like this, NX. Just as I could use NXEY equals 0 here, friends, when it is magnetic, I can say that NXHY equals 0, meaning the magnetic field on the other side is 0. This time, you can use this, friends. But this time, which one can't you use? Who did I say I couldn't use a moment ago? I said I can't use NXH because it will give the current density, so it won't give 0. This time it's the opposite. NXE is not equal to 0 this time, and since the electric field will also give the current density, I can't use it, friends. So NXE equals 0 does not give 0. This also gives JMSI, meaning the magnetic conductor will provide the magnetic flux density and current density. So since it does not give 0, this time it does not facilitate the process, and I cannot use it, friends. The logic of the situation is this, but now I will explain how this opens up according to the incoming wave, and I will give it according to the incoming wave, friends. Don't worry. Lastly, I don't want the video to be too long, so let's quickly see the logic of dielectric transitions. Look here. If it's only PEC from perfectly conducted, I can benefit from the 0 of N cross E at Y equals the exact transition point. If it is PMC, meaning if it is the case where all general fields are reflected, then at Y equals 0, after seeing that it gives H but does not give E, and it will provide the magnetic flux density. You can easily use this in transitions, friends. Now you can do this in these transitions. The first region is again divided into areas like 1 to 2. Let the electric field and magnetic fields of the first region be E1, H1. Let the ones from the second side be E2, H2, friends. And therefore, I can use this here. I am saying that N cross, a normal vector, which I will show what it is shortly. N cross E is where the first region is at Y equals 0, meaning the boundary point S is here, where the exact dielectric transition point is, friends. E equals 0 has given me this. It could also be a X equals 5 would be drawn like this. So, what is important here is the line that changes this boundary, meaning the line that separates the first region from the second region, of course, is the Y equals 0 line. Therefore, what is important for me is that, and I say that N cross the E of the other side, and this time pay attention, there is no 0 field here like there is over there. Here, there is a 0 field because no wave can pass through here. Why can't it pass? Because it extends from the exons to infinity, so there is a direct material transition point here, a dielectric transition region. Therefore, some of the fields will definitely pass here, some will reflect, but the boundary condition I can use is that I say N cross E1 equals, I say N cross E2. Neither this side is 0, nor that side is 0. There are components that are 0 within them, but for now, key is we can use this equality, I equals 0, so we can use it as N cross E1, cross E2 like this. Friends, this is the first. Well, we used N cross E here. For example, we couldn't use n cross a here. Is there such a problem? Or we used n cross a here and couldn't use n cross e here. So can I use both at once? Yes, friends, I can use both at once. I can use both at that boundary. So what is the logic behind it? The logic is very simple, friends. At y equals 0, n cross h is greater than 0 at 0, meaning, do you understand its logic? Let's say this gives a current density on one side, and this gives a current density on the other side. If both provide the same current density, since this also gives the same current density, if both are equal, I can use their equality from here. It is not a problem for me that both are equal in CS here. However, the equality of CS on this side or on that side does not help me directly because I cannot benefit from this 0. But when I look at it this way, there is an equation here, and there is an equation between them. In other words, I can use an equation without involving J. Similarly, let's say this is also equal to JMS. Any JS can be equal. Let it be equal to a flow that is flowing exactly on this surface. Then, since I can use these two, without involving JMS, I can benefit from both of these equations, friends. Let's specify this. So, while my entire equation is here, I can easily perform the operation with this side from this part, and let's choose a more suitable color inside, like this. So, what is this now? How does this open up? What comes from here? What areas come at y equals 0? Let's talk about that right away. Briefly, for example, for the patch in n cross e, we do it like this, friends. If this area were to come diagonally here, like this, what do I want to find for you? I want to find n for you. What is n? How do we decide on this? Look, the logic of my n is similar to the reflection principle in high school physics, in optics, etc. There is a logic that a wave coming like this reflects like this. Right. I am coming perpendicular, honey. But I did this to make the normal vector clearer. Otherwise, I know that the normal vector is minus EE, or along E. Now, if I were to ask you to draw a normal vector for an equation that comes like this and reflects like this, how would you draw it? To separate the incoming angle from the reflected angle. You would immediately draw a perpendicular line here, friends, and this would be your normal line, right? So my question to you is this. In a coordinate system where the horizontal is y and the vertical is x, which coordinate system element does this line I drew represent? Of course, it's negative I, friends. So generally the incoming point is taken, but taking it as positive or negative doesn't change anything. You will see why it doesn't change, friends. Now, do you know why it doesn't change? You can see it very clearly from here. Look, let's say you took A on this side as negative A, there is 0 on the other side. Hold this, throw it to that side, throw these over there. It became negative I and positive I for you, so there is no problem here. Similarly, when you look at these pairs, when it's negative negative, multiply both sides by negative. This becomes positive, and this also becomes positive. Automatically, it still has no effect. Here, whether you take this as positive I or negative I, the important thing is to make the right decision regarding this direction. That is, you shouldn't mistakenly take the normal vector as EX, friends. Therefore, after determining this in some way, it is done like this immediately. Look, you will need to know the cross operation. You will need to know the cross product. You will know it like this. If A is on this side and B is on that side, then A and B give the third direction vector, C. More precisely, if X, Y, Z are involved, the product of X and Y gives Z, and the product of Z and X gives Y. Of course, the direction of these is important, but it is also not important because there is also 0 on the other side. For example, here, let's write this for these two right here. What was our N? We decided it was EY. EY cross E? What is inside E, friends? Let's open a parenthesis like this. We know that EX plus EY plus EZ equals 0. Where exactly? It is green at 0. I couldn't fit this part, sorry. Now, logically, those that are cross products, meaning those multiplied by themselves, are 0 in the cross product. What does the product of A and A give when multiplied with different ones? The product of Y and X gives minus SE, because we take minus in the counterclockwise direction, as you know, but there is no problem since the other side equals 0. If you want, let me move these down a bit. 1 second. Let's bring it down like this, friends. The product of y and x gives z, but again, since the other side is 0, the resulting expression will be, if you want, the product of y and x in the ez direction. In the ez direction gives ex. From here, e cross ee is 0, while e cross ez is plus ex because it is the product of y and z. But it doesn't matter. I'm saying you don't have to write these down. And this is the product of ex and ez. Where are we again, friends? Y equals 0, and 0 is also 0. In fact, this 0 is also represented as we wrote here, ex times ex in the second region, ey times ey in the second region. But since all of these are 0, the fields are on the other side. In a perfect conductor, meaning on the side of our superconductor, the fields are always 0. Actually, the things here seem not to be visible. So from here, similarly, 0 times, meaning the value of 0 for ex2, there are ez's. So if we had written those, you would see that the ez's would simplify, even if we don't write them. When this ez simplifies with this 0, there is a logic of equating separately to 0, because it is a vector operation. Therefore, we write this separately like this, friends. Ex equals 0, and 0 is 0 on its own. Similarly, ez equals 0. Here are two equations that will be useful for you. You can use whichever one you have at hand. Which component is there? For example, in this question, there is the ez component. You know that this gives the polarization value here. This field is of the ez type. Therefore, this question shows that you will benefit from this. I will not do this. I just showed you how this is expanded. If you quickly look at what comes from the expansion of these n crosses, friends, of course, which ones were the results? They were the results coming from PEC. I am not processing quickly at all. You can probably predict that this will come directly from PMC. PMC stands for Perfectly Magnetic Conductor, meaning our super magnetic conductor. So instead of PEC, I used NXA in PEC. Since I will use NXH in PMC and will not use NXA, what will come from here, friends? Guess for me, there will automatically be HX's right. So in this way, Hx equals 0 at 0, and Hertz E equals 0 at 0 as well. Friends, this is the logic of the situation. Let's separate this from here, in this way. I separated it so it wouldn't get mixed up. Now friends, this is within the PEC and PMC. Now if we open these up, what do we get, friends? Our width is still the same, here and on this side as well. It is still coming perpendicular here. If you think it comes like this instead of perpendicular, let's write it with this. It came like this. If you think of it as a wave reflecting like this, if I ask you to draw a normal vector to it, how would you draw it, friends? If I say draw a normal vector like this, you would draw it like this. Which coordinate element does this direction you drew correspond to, x or y? Since it is y, then you have determined n, friends. You have identified the normal vector as e. We identified it as E. The area is coming in the same way. Do not change, friends. In the end, do not see this part. When I do n cross E, who comes? It does not come with Y. E, X, and E, Z come. Then there is a distinction of 1 and 2 here. Because there are areas here I had to write 1 to 2. Since I wrote 1 to 2, the result that will come directly from here is this. Friends, let's write it down immediately. Let's say for dielectric, transition. You can easily write this in these as well. Of course, there is no distinction between PEC and PMC here. We said we can use both. I can use both this and this equation. E is coming for X and Z now. This E does not come specifically for the Y normal vector. The remaining fields with X and Z, excluding Y, are coming. Therefore, I write separately from here as follows. I know that X and Z are coming. Then it comes from the first one like this. E, X is the area of the first region where y equals 0 equals E, X. The area of the second region where y equals 0. This is one of them, friends. Let's mark it like this. 4 equations come from here. What is the second one, friends? Also, Z was coming, if you remember. Ez is equal to the area of the first region where y equals 0. and EZ is equal to the area remaining on the second side of the dielectric transition. This is my second equation. My third equation, of course, you probably won't have X among these, but you will have two equations for EZ. One will come from EZ and one will come from HZ. You will be able to use these. And also H, X will be equal to HX in the first region where Y equals 0, and in the second region where Y equals 0. Finally, friends, HZ must be equal to the first region where Y equals 0, and must be equal at the boundary, in the second region in the dielectric area. Where are these two coming from, friends? Where are these last two coming from? Of course it comes from the uncrosses written in the blue part here. Which one comes from the uncrossed green part, friends? From the part with E as well. E, X, and EZ are coming, just like how E, X, and EZ came from here, how HX and HZ came from PMC as well. Pay attention to the crosses here, separately, and hats came. So if we group it like this, I had done the green part for E. Let's write it like this with green. What shall we call these two? They came from E. What about these two, friends? They came from the cross H that we did here with blue. We said we equalized them separately. The logic is that we processed them separately to 0 in vector sums as well. The same thing applies here. Because we did it separately, one equation was divided into two. The equation with blue H below was also divided in this way. This came from H. It came from N cross H, friends. Generally, the equations and their derivations we benefit from in boundary conditions are like this. I hope to be together with another fundamental video. For now, goodbye, friends. I hope you have understood the logic here to some extent.